Hi, greetings to you all. Welcome to the University of Goroka, SSE 491 STEM Education 1, contextualizing STEM teaching in PNG. Alright, the topic for today's topic for this presentation is all about summary of a STEM lesson. A grade 12 physics lesson integrating STEM. Alright, it's a 40 minutes grade 12 physics lesson bridging traditional Highlands agriculture with modern fluid dynamics. And presenter, I'm Runu Koyazo. Alright, anchoring science in lived experience as quoted by the famous Dr. Marcia Langton. Indigenous knowledge is a vital part of scientific understanding, enriching STEM education with diverse perspectives. The core challenges of physics education is abstract disconnect. This lesson solves that by translating the physics of fluid mechanics through the localized, universally understood lens of Papua New Guinea's agriculture. We will solve the challenges. We can handle the challenges encountered. Lesson architecture and lesson wiring. Curriculum alignment, it's a grade 12 physics. Strand number 2, it's physical sciences, and unit is fluid mechanics. Topic, it's under the broad topic of fluid dynamics. Select the topic. The topic is fluid mass and flow rate. Right? The content standard for this lesson, the SPC content standard is standard 12.2.1.2. It says describe static and dynamic fluid principles and applications. Alright, this is the standards that after this lesson we have to achieve the standard. Alright, some of the essential questions that as we go through the lesson we will answer them in our lesson. Alright, the cultural application, integration of indigenous knowledge. How do traditional farmers in PNG uses the narrowing of channel to speed up flow of water into their gardens? How? In the past, they were good farmers, but when it comes to dry season like this, like today, how do they transport or speed up water into their garden for agricultural purposes? Okay, as we go through the lesson, you will understand. These are some of the questions that you need to bear in mind. Alright, in modern engineering, why is laminar flow more efficient for water conservation in modern agriculture than turbulent flow? Alright, there's two types of fluid flow, laminar and turbulent. As we go through, you will understand laminar and turbulent and the difference between them, and why is laminar more efficient for water conservation in modern agriculture than turbulent flow. You will understand why laminar is preferred over turbulent. Alright. Okay, STEM integration for this lesson, it will integrate adapt sustainability and agriculture and food security. Okay, science, it's basically physics and agriculture in terms of food, gardening. This it involves agriculture, and physics is all the curriculum aligned with the lesson. Okay, conservation of fluid mass and the mechanics of viscosity. Alright, you will understand the conservation of fluid mass and the mechanics of viscosity. Alright, viscosity. What is viscosity? Anyways, as we go through, you will understand viscosity. Alright, technology, materials, comparing traditional bamboo piping with modern PVC or poly pipe systems. Alright, in the past they use traditional bamboo to pump water into the agricultural site or to the house for household uses. These are some of the technology that's traditional technology. Now we have modern technology. As technology increases, they start to introduce PVC pipes, the poly pipes, and all this, and then other forms of transporting the water, like big pipes, the method for not only for water but for other fluids like gas, oil, all this. The engineering aspect is the design, or the engineering is the design aspect of it. Applying the engineering design process to optimize gravity-fed irrigation system. Alright, this is contextualized in the highlands, so it's more applicable in the agriculture where the gravity is the one of the factor that affects the flow of the water. Down in the coastal, this one will be a bit difficult, but out in the highlands, you will see this the importance or uh, uh, the real effect of gravity in work. All right, in the mathematics involves calculating the cross-sectional area of the conduit or the diameter, the flow rate, and these are some of the mathematical stuffs that quantities that requires mathematics and it will be calculated via mathematics. So that's how mathematics is integrated into the lesson. The conduit of physics, the traditional versus modern. Okay, like I said earlier, in the past they use traditional bamboo to pass water through. Okay, but today we use different forms of pipe like PVC, the poly pipe, and so on. Right, the material design that in the past the traditional approach they use organic bamboo conduits, and today we use extrude PVC poly pipes, and then in the past they use surface interior. The natural nodes for traditional, it's a natural nodes and rough walls. It's a rough walls where it it does not tolerate a steady flow, where that's where turbulence flow is represented here. And then the PVC are modern system, perfectly smooth cylindrical bore. There's nothing turbulence there. It's all laminar flow. Okay, dominant flow types, high turbulence in traditional, and in modern, it's a laminar efficiency. It's a laminar flow. All right, energy loss high in the traditional system, and in the modern system it's low. Contextual application, subsistence highland saturation, and in that's traditional. But in the modern, it is applicable to both highlands and the coastal because the system is more better than the traditional one. It does not rely heavily on the gravity, but some other forms of energy that helps to push the water, the fluid, visualizing the continuity equation. One of the special equation in fluid dynamics is the equation of continuity. In the equation of continuity, it says that A1 V1 must be equals to A2 V2, where A1 is the area, let's say point 1 and point 2. These are the 2 points. Alright, area 1, velocity 1 must be equals to area 2, velocity 2. Okay, this one, it's true. 2, because when water enters the pipe, it's fixed. The flow rate is fixed, so it has to be fixed throughout. So the volume the flow rate must be constant throughout. So in order for that, you will see that in area 1 is bigger than area 2. Then in area 1, where the area is bigger, the velocity is lower. And in area 2, where the area is low, the velocity is higher. That caters for the flow rate, or it keeps the flow rate consistent from point A to point B despite the differences in the cross-sectional area. Because fluids are incompressible, narrowing a channel forces the water to speed up to maintain a constant flow rate where Q1 must be equal to Q2. That's what I just said in two different surface areas. Alright? The engineering hurdle, laminar versus turbulent flow. While the continuity equation dictates speed, the material dictates efficiency. Alright, continuity equation. A1 V1 equals A2 V2 dictates the speed of the water, but the material dictates the efficiency. Whatever materials you use dictates the efficiency. For laminar flow, it's efficient. For the modern system, it's efficient because it's a laminar flow. But for turbulent flow, for traditional system, it's a turbulent flow, so it's energy loss. So efficiency is it's very low. Right. To connecting this lesson, students learn through rough surfaces like traditional bamboo nodes, create turbulence. So you connect this. You will connect this knowledge to your previous knowledge on traditional engineering, the traditional system of conduits. You will see that there's some boreholes, blockades where the join of the bamboo is. So this acts as a barrier and then it creates energy loss or it causes turbulence flow. Okay, unlike the modern system where the flow is steady throughout, a laminar flow through. Right, it's a 40-minute lesson execution time. The lesson flow timeline. The introduction is a cognitive phase, contextualizing the PNG context, the highlands specific action, connecting the physics of flow to the local garden irrigation and flood surges. Okay, the second phase is the modeling. A teacher demonstrates the continuity equation A1 V1 equals to A2 U2 by using the narrowing pipe. Okay, we will have a drawing of a pipe where we will apply, we will use the try to demonstrate the equation of continuity where A1 V1 equals to A2 U2 by using a narrowing pipe. Cognitive phase, phase 3, is applying and designing. This one is engineering design. A guided highlands terrace velocity calculations and 10 minutes independent sketching, laminar irrigation success. Conclusion, cognitive phase synthesizing, connecting the fluid mass conservation back to the common good of the sustainable farming. Okay, the assessment part, the part to the mastery of the lesson will be step 4 out of, or will be given out of 10. So for the advanced level, it's engineering leap correctly applies the continuity equation to all scenarios and justify the design efficiency based on laminar versus turbulent properties. Good. 10 on 10 for this one. And proficient, which is consistently use A1V1, the continuity equation to solve for velocity, accurately define steady flow. Then you get 8 on 10. And partially proficient with 5 on 10. Solves basic flow rate problems, U equals to AV, but lacks clarity on laminar versus turbulent definitions. Then you get 5. And below that, it's no issue. Students struggle to apply formula, cannot connect concepts to PNG agriculture, then you get 3. And below that, you get less than that. Okay, the evolution of engineering, the constancy of physics. A1 V1 equals to A2 V2. That's the equation of continuity. And as we go through the lesson, you will understand the equation of continuity and how to apply the equation of continuity to real life problems and in all other aspects of STEM, in engineering, mathematics, science, technology, and how to apply this uh, content knowledge. All right. With that, thank you for your time and participation, cooperation, and see you all. Bye for now.